Hello students, I am Dr. Satish Chauhan, your chemistry tutor. In this video number 5, you will learn the physico-chemical principles in the manufacture of nitric acid and uses of nitric acid from the chapter number 3, that is manufacture of basic chemicals. Physico-chemical principles in the manufacture of nitric acid. There are 3 important steps involved in the manufacture of nitric acid. Number 1, oxidation of ammonia to nitric oxide, oxidation of nitric oxide to nitrogen dioxide. Number 3, absorption of nitrogen dioxide in water to form nitric acid. Let us consider the physico-chemical principles involved in the oxidation of ammonia to nitric oxide. The most important step in the manufacture of nitric acid by Ostwald process is the catalytic oxidation of ammonia to nitric oxide, which proceeds by the reaction 4 ammonia plus 5 O2 that gives 4 NO plus 6 H2O plus 950 kilojoules of energy. The reaction is reversible and the forward reaction is exothermic. Here 9 volumes of the reactant gives 10 volumes of the product. Thus, there is little increase in the volume when nitric oxide is formed. Let us consider the effect of temperature on the oxidation of ammonia to nitric oxide. Since the reaction is exothermic, it is expected that low temperature will favor this reaction. However, at lower temperature, the rate of reaction is slow. So, an optimum temperature of about 750 degrees Celsius is kept when pressure is 6.8 atmospheres. At higher temperature, there is a tendency of ammonia to get oxidized to N2 and decomposition of NO2. Thus, efficiency of process is decreased. The catalyst is only initially electrically heated to about 800 degrees Celsius and then the reaction continues on its own maintaining temperature. Effect of pressure. The forward reaction proceeds with a little increased volume and backward reaction proceeds with little decrease in the volume, that is 9 volumes, these are giving rise to the 10 volumes of the product, and 10 volumes of the product, these are giving rise to the 9 volumes of the product in the reversible reaction. If we increase the pressure, equilibrium will shift to the small extent to the left, decreasing the yield of nitric oxide, but there is some advantage in increasing pressure. If we increase the pressure, the space velocity, that is volume of leaving gas corrected to NTP conditions, which passes over the 1 cubic foot of catalyst per second, increases, and hence larger volume of the gas is converted by the small volume of the catalyst. Thus, small proportion of catalyst is sufficient. For further reaction, increase of pressure shifts the equilibrium to the right. Hence, the larger amount of nitric acid is formed at high pressure. The pressure applied in practice is 6.8 atmospheres. Effect of catalyst. It is found that when catalyst is taken in the form of gauze, it is more effective. A multilayered catalyst made of 10% rhodium and 90% platinum is taken in the form of 80 mesh gauze. The weight of gauze is 105 ounces, which is critical. There are about 20 layers of this gauze used as catalyst. The conversion of NH3 by volume mixed with preheated air at 300 degrees Celsius takes place through this catalyst at a temperature of 750 degrees Celsius. The yield of nitric oxide is about 94 to 95%. Effect of proportion of the gases, that is NH3 and air. The effect of the excess of oxygen should be taken because some oxygen is also required for the conversion of nitric oxide to nitrogen dioxide. Generally, the mixture of 10% NH3 and 90% air by volume is taken. If the proportion of ammonia in the mixture exceeds than 10%, there is a danger of explosion because the reaction takes place under high pressure. Similarly, many side reactions may occur that reduce the yield of nitric oxide and more NH3 is wasted. Rate of flow of gases. In the reactor, all ammonia should get oxidized at once, otherwise second reaction between unused ammonia and nitric oxide produced in the main reaction. So, that will give rise 4 ammonia plus 6 NO, that will give nitrogen evolution in the reaction. So, the gases should not remain in contact with the catalyst for a longer period of the time. The rate of flow of gases should be high. For platinum rhodium catalyst at 750 degrees Celsius, the base time of contact is 0.0014 seconds. If the contact is longer, nitric oxide is decomposed to N2 and O2. Let us consider the next step, the principles involved in the oxidation of nitric oxide to nitrogen dioxide. Here is the reaction. The nitric oxide is reacted with the oxygen, undergoes oxidation, gives 2 NO2. The 3 volumes of the reactant giving rise to the 2 volumes of the product with evolution of 114 kilojoules of energy. This reaction is also a reversible reaction. Forward reaction is exothermic and there is decrease in volume when nitrogen dioxide is formed. According to the Le-Chatelier's principle, high pressure and low temperature is favorable for the oxidation of nitric oxide to nitrogen dioxide. This conversion of nitric oxide to nitrogen dioxide takes place at 150 degrees Celsius and 6.8 atmospheric pressure. Since the reaction is slow, more contact time is necessary for oxidation. Principles involved in the absorption of NO2 in water. Absorption being slow process, more space is required for the absorption. Absorption of NO2 by water under the control process gives nitric acid. The forward reaction is exothermic, hence the rate of reaction can be increased by cooling the gases to 40 degrees Celsius to 50 degrees Celsius, employing counter current graded strength of acid for absorption. The nitric acid produced in the Ostwald process is about 61 to 65% in strength. The thrice NO2 plus H2O, that gives twice HNO3. That is the reaction taking place when nitrogen dioxide is dissolved in water. Thus, the favorable conditions for the better yield of nitric acid are temperature 750 degrees Celsius for the conversion of ammonia to nitric oxide and 150 degrees Celsius for the conversion of nitric oxide to NO2. Pressure 6.8 atmospheres. Catalyst 10% rhodium, 90% platinum gauze catalyst. Proportion of the gases ammonia to oxygen, ammonia 10% and oxygen 90%. Important uses of nitric acid. Nitric acid plays a significant role in the manufacture of various products such as explosives like trinitrotoluene or TNT, nitroglycerin, gun cotton and ammonal. It is used in the fertilizer manufacture such as calcium nitrate and ammonium nitrate. Nitrate salts such as calcium nitrate, silver nitrate and ammonium nitrate. It is used in the manufacture of dyes, perfumes, drugs, etc. from the coal tar products. Nitric acid is used in the manufacture of sulfuric acid by lead chamber process. Nitric acid is used in the purification of silver, gold and platinum, etc. Nitric acid is used in the etching designs on copper, brass, bronzeware, etc. It is used to prepare aqua regia to dissolve the noble elements. It is used as a laboratory reagent.